Okay. So we will start this exercise session with the exercise 3. So in the exercise 3, it is about conditional expectation. So we take a G, which is a sub-sigma field of some sigma field F, which is fixed on some probability space, and X, which is an independent random variable of the sigma field G. And the law of this random variable is denoted by Px. So it is the usual notation that I will use. The P with the index of the random variable means that it is a law of the random variable X. And we consider some other random variable Y, which is a G measurable. And we define some Z, some new random variable Z by Z, which is some deterministic function phi of X and Y. And so the goal is to show that the conditional expectation of Z given G is given by the formula which is written here. Okay. So let us start. So it is exercise 3. Okay, exercise 3. So what we have is that X is independent of G, of the sigma field G, and Y is G measurable. And we are considering the random variable Z, which is some deterministic function phi of X and Y. And so we need that we want to compute the conditional expectation of Z given G. And in this exercise, there is some precise formula for that. So we have to come back to the definition of what is a conditional expectation. What is this guy here? So this is a random variable, which is G measurable, and it is a unique random variable, which is G measurable, such that when you compute the expectation of Z times G, where G is any G measurable random variable, that we can take bounded, for example, random variable. We will assume that it is bounded. So we have to compute this expectation of Z times G, and by computation, we have to conclude that it is equal to the expectation of some random variable here, not by dot, times G, but this dot has to be a random variable which is G measured. And this dot, if it is true for any G, it will be the conditional expectation of Z times G, Z given G. Okay, it is a definition of the conditional expectation. So let us start. We have expectation of phi xy by definition G. Okay, so it is expectation of some function of 3 random variables x, y, and g. So I can write it like by using what is called the transfer formula. I can write it like the integral over small x, small y, small g of phi x, y, g integrated against the law of the vector x, y, g of x, y, g. Okay, it is a transfer formula. You know this transfer formula, which is to express the expectation in terms of the law. So for example, if it is the law as a density, instead of this guy which is here, you will write the density in x, y, g times dx, dy, dg. But it can be also, if the random variables are discrete, then it is, this integral is in fact a sum and so on. Okay, it is just a measure theory general framework. And now what we know is that x is independent of g, y is a g measurable, and g is a g measurable. So it means that, in fact, in this expression, here you have yg, which is independent of x. So it means that the law will be factorized. So we can write it like the integral over x, y, g of phi x, y, g. So since x is independent of y and g, we have this property that you can factorize the law. It becomes a product measure. Okay, because x independent of g and yg here, and yg is a vector which is a g measurable, which implies that in particular that x is independent of yg. Okay. And so now at the end, if I remember what I want to get some expression like that. So I will isolate the g and the x. So I will write it like the following way. I can write it like the integral over g of the integral over x and y by Fubini's theorem, xy dp xx g dp y g y g. Okay, just by Fubini's theorem. Okay, let's try to do like that. So we have his expression. Now we continue. Now, okay. In fact, you see, is okay. I can in fact write it in a different way. Tac, g and y here. In fact, because here I am with his expression, which is here, I'm integrating only on x. Okay, where x and y is fixed. So in fact, again, by the transfer formula, I can rewrite this integral like the expectation of the integral over x of phi small x capital Y dpx x g like that. It's again by transfer formula. Okay, because here, in fact, what you have here, you have some deterministic function of small y times g, and you integrate respect to the law of the random variable yg. So you get this formula, and here you see that this guy is a function of y. And since it is a function of y, and y is j measurable, so that, in fact, this random variable here is a g measurable. So it is exactly what I wanted. I wanted to rewrite this expectation of z times g. I wanted to write it like the expectation of some random variable, which is here represented by the dot, which is g measurable times g. And it is exactly what I did. See, it is the expectation of some random variable, which is g measurable times g. And it is true for any g, which is g measurable. So I use the fact that g was g measurable here, because when I say that yg is a g measurable, so that x is independent of yg, it is there that I use that g was g measurable. So the conclusion is that the expectation, conditional expectation of z given g is just the integral over x of phi x y dp x x. So is it clear for everybody, or are there some questions, something which was not clear in the explanations?
All is clear.
All is clear. Okay, perfect. So this formula is very useful sometimes to compute conditional expectation. So here it is valid for any random variable with discrete law or with continuous law with density respect to the Lebesgue measure. It is a general formula. Okay. And so when you want to compute some conditional expectation, usually you have to come back to the definition. This is what we did here. Okay. Let us continue maybe with the second exercise, exercise 4, in which you have some random variable x, which is distributed like a normal random variable with mean 0 and variance sigma square. And we take a z, which is just a function, pattern function of capital X and Y, where X and Y are independent random variables. Y is independent of X. And the question is compute the conditional expectation of z given Y. So let me rewrite what is z. So it is exercise 4. So z is exponential of, I forgot, it was what? Exponential minus sigma square root 2y square plus xy. And x and y are random variables, independent. So that we write it like that, usually. X independent of y. And the question is, first question is expectation of z given y. Okay, when we write a z given y, in fact, it means z given the sigma field generated by y. So it is the same notation as to write a z given sigma y. So how you do that? In fact, it is very simple. In fact, it is like if y was fixed, because in fact, I use the previous formula that we proved in the previous exercise. You see z is a function of x and y. This one here is sigma y measurable, of course. And this one is independent of sigma y. So we are exactly in the context of the previous exercise. So I have some formula for this, this quantity. It is the integral in x, so capital Y will be fixed, of exponential of minus sigma square divided by 2 y square plus small x times y dp x x. Okay, and now what is the law of dpxx? I know what it is because we know that x is some normal variable which means 0 and variance sigma square. So I know that this dpxx, in fact, this dpxx is in fact given by 1 over square root of 2 pi sigma square exponential of minus x squared divided by 2 sigma square dx. Okay, this guy here, I replace it by its law, which is given by this density. And here in this formula, you see it is this guy is a random variable, of course, because here you see that the y is a random variable. So it is some interval with the parameter where y is like a parameter, a random parameter. So now we have to compute that. And to do that, I first perform some some change of variable. I take x divided by sigma equal to t. So dx divided by sigma is equal to dt. So you observe that here there is a square root of sigma square, which is exactly this sigma. So I get that this is equal to the integral over r exponential minus sigma squared divided to y squared, which is just a constant. Exponential of now x is equal to sigma ty, 1 over square root of 2 pi, exponential of minus t squared divided by 2 dt. And in fact, since this guy is something independent of t, okay, it is just a parameter. So in fact, I can put it outside of the integral and put the integral here. Okay, and so now I have to compute this guy, which is here. And if you look at this guy, you recognize, in fact, the Laplace transform of some standard Gaussian random variable, where the parameter of this Laplace transform is a sigma t. Sigma y. Okay, it is a t, which is a variable that we are. It is the variable that we are integrating. So we know that, in fact, that's the expectation of lambda t 1 over square root of 2 pi exponential minus t squared divided by 2 dt over r. It is well known that it is equal to exponential of lambda squared divided by 2. Okay, so in fact here, what I get by using this result is that this guy is equal to exponential minus sigma squared divided by 2y squared. And I replace with this formula that I recalled, the exponential of sigma square t square sigma square y square divided by 2. And so you have some simplification, and that at the end it is equal to 1. Okay, and expectation of z given y is just a constant, is equal to 1. Questions about that, or is it okay? Yeah.
Yeah, it's
so
okay.
Okay, if there are some questions, you can interrupt me when I'm performing the computations. Okay, and so the second question I think was to compute the expectation of z. Let me see. It was that. Yes, expectation show that the expectation of z is equal to 1. But that is completely trivial, because you see we know that the expectation of z, okay, it is the main properties of the conditional expectation. It is expectation of the expectation of z given y, and so it is expectation of 1, which is 1. Okay. Okay, good. So let me continue. So in principle, I think that this kind of thing you should more or less know how to do it, that you have seen previously in your previous courses. But I prefer to be sure that everything is clear now, because later we'll use some conditional expectations several times, so it has to be completely clear. So I propose now to do okay, maybe it's exercise 6. So we have some random variables which are all independent with a mean which is fixed mu, and they are IID, independent identically distributed. And we denote by Sn, which is a sum of the xi from I equal 1 to factorial n. And okay, it is written that by using a symmetry argument, show that for every I, we have that the conditional expectation of xi given Sm is equal to Sn divided by n. So, okay, let us prove that. So exercise 6. So x1, x2, xn are IID with mean Sn is equal to x1 plus x2 plus xn. And so in the first equation, we take here, we have to compute the conditional expectation of xi given Sn. Okay, so I didn't mention previously, but of course, all the conditional expectation exist if the random variable are interrogable. For example, here, this conditional expectation exists because xi are assumed to be with mean mu, so it means that they are interrogable. So this conditional expectation always exists. So now, to do that, okay, we have to use some symmetry argument. Okay, there is something which is very simple, is that the expectation of Sn given Sn is equal to what?
Sn.
Yes, exactly. Okay. Because you see, it is very intuitive. The conditional expectation is the best approximation that you can have of Sn, given that you know Sn. So of course, if you know Sn, the best approximation of Sn is Sn. But it is also some property of the conditional expectation, since Sn is sigma Sn measure. Okay, so it is this one, and now by a linearity of the conditional expectation, because Sn is a sum, so here I can replace Sn by the sum, and I can say that it is a sum over I equal 1 to n. Okay, maybe I is fixed here, so I prefer to call it j. Expectation of xj given Sn. Okay. But now, you see all the xi have the same, as this RIID, and they have the same law and are independent. So in fact, the idea is that this guy, in fact, is independent of J. Okay, so it is quite intuitively, it is quite clear, but maybe it is, okay, if you want to justify why this guy is in fact independent of J, what you can do is the following. You can say that if you take that called sigma, which is, or tau, maybe it is better. Tau, which is the permutation on 1n, which is a transposition, in fact, which is given by is the following. So I is equal to say k. Tau k is equal to I, and tau L is equal to L for L different from IK. Okay, just, okay, probably I fix I and K, and I define some transposition between I and K, just a permutation which exchanges K with I, and we let the other integer invariant. And then, since x1, xn are IID, and it means that this vector has the same law as x, where you permute according to this tau ik1, x to ikn. They have the same law. And of course, this Sn is completely invariant by this tau ik. When you permute the indexes of the xi, then you don't modify the sum. Okay, so here there's the same law, so it means that in fact this implies that xi Sn has the same law as x to iki Sn. Because the S, when you permute the coordinates of Sn, you don't modify Sn. Okay, and so since you have that, it implies that since this quantity, in fact, this conditional expectation depends only on the xj and the Sn. Okay, it is just depending on these two random variables. So it means that the conditional expectation, okay, if this one is equal to xk by definition of 2ik Sn, so it implies that the conditional expectation of xi given Sn is the same as the conditional expectation of xk given Sn. Okay, so it is just justification of something which was probably very obvious for you, that this quantity is completely independent on j. And so since it is independent of j, it is the same for every j. So for example, for I, and so we get at the end that Sn is equal to n times expectation of xi given Sn. Okay, what I did here was valid for any pair ik, distinct pair of I and k, also for I equal to k, which is evident. So at the end, we get well that the conditional expectation of xi given Sn is equal to Sn divided by n. Okay, without any computation. Not so much computation, at least. Is it clear, or there are some question?
It's okay.
It's clear. Okay, perfect.
It's clear.
Okay, I think that's what is the second question in this exercise. It is, let's see. Okay, we fix m less than n, and we have to deduce the law of Sm given Sn. And m is less than n. Okay. So okay. M is less than n, and we have to compute the conditional expectation of Sm given Sn. So it is an expectation of sum from I equal 1 to m of xi given Sn. And this is equal to, by linearity, it is a sum from I equal 1 to n with expectation of xi given Sn. But since I is less than n, it is less than n. And so we have seen previously that this conditional expectation was independent of I and just given by Sn divided by n. So at the end, we get just m divided by n Sn. So not difficult. Okay. So, okay. So let us come to something maybe more involved. Still time to do this one. Yeah, probably it's better to do this one before. Okay, so here it's just so exercise 7. It is the notion of conditional variance. So we have the conditional expectation, but there is also some notion of conditional variance, which is a variance of y given x. So to be well defined, you need that y is in L2, so it has a second moment, so that you can consider the conditional expectation of y squared given x. And so the first question is to show that this variance of y given x is a non-negative random variable. So do you know how to prove it? What kind of thing you have to use to show that it is non-negative random variable? So this guy.
Yeah. Maybe it should be not okay. No.
So do you know how to prove that the variance is positive? The usual variance, the variance of y, which is the usual variance. I mean, which is variance of y.
It is by definition.
Yeah, it is by definition the expectation of the square of the difference of the our y and its mean.
Some difference.
Yes, it's true that you are right, because here I wrote it. It is true that the variance is also equal by linear. It is just a consequence of the linearity. It's like that. Is a formula that you told me. This one, the second one. But you know that there is also some second different expression, which is this one here. And imagine that you don't know that this guy is equal to this guy. Do you have some idea how to prove that without using this information that you gave, to prove that it is positive? So if it is positive, it means that the expectation of y square has to be smaller than the expectation of y square. Some inequality between expectation of random variables.
Yeah, it's like a Cauchy. It's Cauchy.
Yes, it is Cauchy-Schwarz, exactly. So because Cauchy-Schwarz, you see, you can write expectation of y. You write it like expectation of y times 1. Okay, so it is a product of two functions, and by Cauchy-Schwarz inequality, you know that it is smaller than the square root of the expectation of y square root of the expectation of 1 square. And this guy, of course, is just 1. Okay, so I can erase it. And here it is there is square root, but now if I take the square on both sides, I get that expectation of y square, which is here, is smaller than the expectation of y square. So in order to prove that, if you are right, you use Cauchy-Schwarz. Okay, but of course, in this case, you can also show that. So that becomes also true. So the idea here is to use this kind of Cauchy-Schwarz, but for the conditional expectation. So I think that it is in the principle you should know this kind of what is called, in fact, this Jensen inequality, conditional Jensen inequality. Because Cauchy-Schwarz is a particular case of Jensen. So let me recall you that, and to prove that this variance, conditional variance is positive, but the idea is the same. So I don't remember what was. So exercise is number 7. Okay, so exercise 7. So I just recall that if psi, say from R to R, is convex, and if X is a random variable, such that E of X is finite, and expectation of absolute value of psi X is finite, and And if G is some sigma field, you have the Jensen inequality. Then I should say we have the conditional Jensen inequality. So as you know, the Jensen inequality is just that psi of the expectation of x is less or equal to the expectation of psi of x. Yeah. So it is a Jensen inequality, and particular case, it is when psi of x is x squared, which is a convex function. And if you use with this function psi squared, you get that the expectation of x squared is less than the expectation of x squared, which is also Cauchy-Schwarz inequality. It can be deduced also Cauchy-Schwarz inequality, but probably you know that in fact when you want to derive Hölder's inequality, what you do is that first you prove Jensen inequality and then the Hölder's inequality, and in particular the Cauchy-Schwarz inequality is a consequence of Jensen inequality. So Jensen inequality is really the basic inequality from which you can derive the other inequalities like Hölder's inequality. So this is the usual Jensen inequality. What I mean that by conditional Jensen inequality is that this property is also true by replacing the expectation by the conditional expectation. So here I replace this expectation. Sorry. And you get what is called this conditional Jensen inequality, which is some inequalities between random variable. Because here this guy is a random variable and this guy is a random variable. Okay, which are G measurable. So I think it is in the properties which are listed in this sheet about the properties of the conditional expectation. Okay, and it is this one that we will use, this conditional expectation, these Jensen inequalities with a function psi x is equal to x squared. If I do it, I will get exactly that expectation of x given G squared is less or equal to the expectation of x squared given G. And so you see it is this proof that the question one, which was that the variance is the variance, the conditional variance is a positive random variable. Okay, just here in the exercise, we see it is just the G. Here it is sigma x, in fact, and my previous x was the y. Okay, but so it proves it is a way that we prove that it is a non-negative random variable. Okay, so this conditional Jensen inequality is very useful. And okay, so it proves the question one. Everybody agrees with that? Yes.
I agree.
Okay. Good. And now we have to show the second property, that the expectation of the conditional variance is a variance, that's the real variance which is written here, minus variance of the conditional expectation. So let us prove this second fact. So we have to compute the expectation of the variance of y given x. Okay, the conditional variance of y given x is a random variable. So by definition, it is expectation of the expectation of y squared given x minus the expectation of y given x squared. Now the expectation is linear, so I can write it like the expectation of y squared given x minus the expectation of this random variable exponential of y given x squared. Okay, the first one is easy because the conditional expectation, the expectation of the conditional expectation is the expectation of the random variable itself. So it is the expectation of y squared. And okay, now if
why not y squared depends of x with condition?
you mean
okay, yeah, sorry, I agree.
Here I use some property that you know
It's okay.
It's okay. The expectation of z given g is equal to expectation of z. It is a general property valid for any random variable z and any sigma field g. Okay, so now if you remember what we want to create to obtain the variance of y minus the expectation of the conditional variance. So I inject here, I plug this exponential of y squared in order to create the variance of y. Okay, this guy is not here, so I add it now. And there is the last guy, which is still here, which is expectation of y given x squared. Okay, so I recognize first variance of y. And now if you look at what we want to prove in the second term, which is here, we should see, according to what is written here, it should be the variance of the conditional expectation. So I have to see if this guy like the variance of the conditional expectation. So here I have the expectation of the random variable square, but so it means that here I have to replace this guy by this guy here. I have to replace it by the expectation of the square of the conditional expectation. That is true. I can write this guy like the expectation of the expectation of y squared given x. It is again the same property that I used previously, which is, I mean, this property here I used again here in order to replace this guy. I say it is the same as the expectation of the conditional expectation, and the second guy is still here. So it is expectation of y given x, everything square. And so if you look carefully at this guy, you see that it is the variance of the random variable. It is a I can rewrite it again a bit. It is variance of y plus the expectation of what? Of the expectation of y squared given x minus the expectation of y given x squared. But this is precisely the variance, the conditional variance of y given x by definition. And so it proves the second claim. Okay, the expectation of the conditional variance is the usual variance plus the expectation of the conditional variance. Wait, no, there is something which is wrong. What I did here?
Maybe the typo.
Yes, I made a typo, yes, because it is completely stupid what I did. Wait, no. So that is correct, and here it is the expectation of y squared. Yes, it is. Yes, it is a bit.
It is a variance. Variance should be at the beginning.
Yeah, it is. It is a variance here. Here it is a variance, yes. That is a variance.
Yeah, and at the last term, you should start with the variance. Like, I mean, variance of y plus
But it's not
variance of
equal.
mathematical expectation of y when x. Yeah.
You mean this term here, which is not correct.
No. There's the like
That's
after
correct.
the last term should be like variance of expectation of
okay.
y when x.
Okay. Yes. Okay. So I write it like okay. I agree. You're right. It is. So I put the last guy. It is expectation of y given x square. So I want to recreate the expectation of what I want to create. See, minus the variance of expectation of y given x.
But we proved previously that like the sub at the line next to the bottom line, like their expectation of y squared when x minus expectation of y when x squared, it is equal to the variance of expectation of y when x. Yeah, I suppose.
The previous time we just proved that it was positive. So here we have just to recognize here what we claim. The claim is that okay, there is this vy here. So you agree with the vy. I introduce this minus.
Yeah.
This one is okay. Yeah. So up to here you agree. Everything is correct.
Yeah.
Okay, so now the claim is that this guy should be the last guy, the two last guys, which are here. It is minus the expectation of the conditional variance. So I write it like that. I write first the last term is expectation of y given x square, okay, minus, okay, now I have to rewrite this expectation of y square, but this expectation of y square, okay, I write it like it's expectation of the expectation of y given x, which is just the expectation of y. No, okay, now I understand. Okay, I see you. So here it is, the square is outside, you see? But here I put it inside. So it's the reason for which it was completely, you see? I subtract this guy and I add, but they are not the same. So it is the reason for which there was a mistake. Okay, the square is outside here. So now, okay. Now this expectation of y square, it is, I use again that's the expectation of y, which is this one here. I write it like the expectation of y given x. So it is expectation of the expectation of y given x. So this guy is just expectation of y. And now everything is square. You agree with that now? Because what I did here, this guy here is just the expectation of y.
Yeah, okay.
Okay. And so now we have recognize what we wanted is variance of y minus the expectation of the variant. It is, sorry, it is now it's not expectation, it is minus
Just
the
the
variance.
definition of variance. Yes.
Exactly. Variance of the expectation of y divided x. Okay.
Okay.
Just not to be lost in the. Okay.
Yeah, okay.
Okay, so we will use that in the next exercise, which is about some what's called gauge processes. So let's go to this next exercise, which is exercise 8, in which you have some so you have some stochastic process, which is in fact a Markov chain. So it is defined in the following way. It appears in the time series, a financial time series. It's very useful for some model of time series in finance. So it is a discrete time process. So xn are a collection of random variable, and it is defined in the, so it represents, for example, the price of some asset at time n, and the evolution of this price of the asset at time n depends on the previous price at time n minus 1, but it is affected by some random variable epsilon n, which are all IID, okay, and which are mean 0, they are centered, and with variance 1. So you see, if you look on alpha 0 and alpha 1 are just a positive constant. So you see that xn is in fact some function of xn minus 1 and epsilon n. So that is a general form of some Markov chain, homogeneous Markov chain, which here the epsilon n are IID. So it means in particular that xn minus 1, you see by constriction, xn minus 1 will depend only on epsilon 0, epsilon 1, epsilon 2, epsilon n minus 1, because it is constructed by recursion like that. And so this random variable epsilon n will be independent of this xn minus 1. So you can prove it by recurrence. Okay. Okay, so the first question is to, okay, we did not by
But
fn.
why we use two indexes here, two indices, two different?
You mean n under n minus 1?
No, n and m.
No, there is no n.
Ah, okay, it looks
here.
like m. Okay.
I'm sorry, maybe it is a quality of the. It is the same n. N is
No, in what you wrote with the red mark.
So no, it's maybe it's like that.
Okay.
Okay, sorry.
Then okay.
No, it's the same. Okay, and this is the natural filtration. You remember that the filtration represents the information that you have, and it is some sequence of increasing sigma field, and here it is increased with n. So in particular, we see that, in fact, okay, so maybe it is good to write just the first. You see, you have x0 first, x1 is epsilon 1 square root of alpha 0 plus alpha 1 x0 square, x2 is epsilon 2 square root of alpha 0 plus alpha 1 x1 square, and so on. So in fact, this fn is a sigma of x0, x1, xn. But in fact, you see, you have the same information. It is also the sigma field generated by x0, epsilon 1, because x1 is in fact a function of x0 and epsilon 1, epsilon 2, and xn is epsilon n. So in fact, the natural filtration of x is the same as the natural filtration of the epsilon, where you add the initial condition x0. Okay.
Do we know anything about x0?
No, we don't say nothing. It is just a random variable, which is initially something. Can be deterministic or can be random. But it is independent of the epsilon n. Did I say something like that? Okay, maybe I forgot to say. No, I said independent of x0. Okay, so the epsilon x0, epsilon 1, epsilon 2, epsilon n, they are all independent. Of course, it is not true that x0, x1, xn are independent. They are not independent. In fact, they form some Markov process. Okay, so let us show that. First question is to show that the conditional expectation of xn given fn minus 1 is equal to 0. So I wrote okay. Yes, 8, I think. So I rewrite just the definition. Xn is epsilon n square root of alpha 0 plus alpha 1 xn minus 1 square. And fn is sigma of x0 xn, which is the same as the sigma of x0 epsilon 1 epsilon n. So the first question is to compute the expectation of xn given fn minus 1. So let us use the basic properties of the conditional expectation. So you see it is by definition it is conditional expectation of epsilon n square root of alpha 0 plus alpha 1 xn minus 1 square given fn. So it is given given fn. But you have to remember that fn is phi sigma field. So what we observe is that this random variable epsilon n, you remember that the epsilon k are all independent. So in particular, sorry, it is here, there is some n minus 1. Yeah, thank you. Yes, so this epsilon n, in fact, is independent of this fn minus 1, while this quantity here is fn minus 1 measurable, because in fn minus 1 you have, if you replace n by n minus 1, you have xn minus 1. Since it is a function of xn minus 1, this guy is measurable with respect to this sigma field. So in fact, it means that it can go outside of the conditional expectation. So it is square root of alpha 0 plus alpha 1 xn minus 1 square conditional expectation of epsilon n given fn minus 1. So this equality is because square root of alpha 0 plus alpha 1 xn minus 1 square is fn minus 1 measurable. Okay, so you agree that it is fn minus 1 measurable. It is a function, deterministic function of xn minus 1. So it is, you have the information xn minus 1 in fn minus 1, so it is measurable with respect to this sigma field. Okay, and here I use the property of the conditional expectation, that what is measurable with respect to the sigma field can go outside. And this one, now, here, I will use that this guy, this random variable epsilon n, is independent of this sigma field by definition, because this sigma field is generated by this random variable until n minus 1, and the epsilon 1, epsilon 2, and so on, they are all independent. So in fact, when you have the expectation of a random variable which is independent of the sigma field, this conditional expectation is constant and coincide with the expectation. So this guy is in fact just square root of alpha 0 plus alpha 1 xn minus 1 square, expectation of epsilon n. And so here, because epsilon n is independent of fn minus 1. And so now, by assumption, we assume that the epsilon n are centered, so their expectation are 0. So it is 0. Okay. Is it okay for everybody, or is there some question? I use two fundamental properties of the conditional expectation is this computation.
Yes, it's clear enough.
It's clear? Okay, good. So now what is the second question is, so we introduce now this conditional variance. So it is a conditional variance yn square. Okay, we can write yn square because we know that the conditional variance is positive. It's a conditional variance of xn given fn minus 1. And so we have to establish this equality, and we will use, I think, probably something like that. Because here it is a conditional variance. No, maybe not. Okay, maybe we'll use such as definition. Okay, so let us compute this variance of xn given fn minus 1, conditional variance. So yn square is the conditional variance of xn given fn minus 1. Okay, so by definition, what is this conditional variance? It is the expectation of xn square given fn minus 1 minus the expectation of xn given fn minus 1 square. Okay, it is the same definition as the usual variance, but you replace the expectation by the conditional expectation. Okay, but by the question 1, we know that this guy is equal to 0. Okay, so we don't have to take care about this guy, which is 0, and it remains only this guy. And this guy, okay, we can use the definition of what is xn square. So I use the definition of in terms of xn minus 1. So there is a square, you have to take the square. So it is expectation of epsilon square, alpha 0 plus alpha 1, xn minus 1 square, given fn minus 1. Here again, I can use the same properties as before. This random variable, which is here, is measurable with respect to this sigma field, while this one is independent of this sigma field. So I get that it is alpha 0 plus alpha 1 xn minus 1 square, expectation of epsilon n square given fn minus 1. Okay, same argument as before. And now, if you remember that we assume that epsilon is centered and the variance of epsilon n is equal to 1. So, okay, so now this guy is in fact equal to the expectation of epsilon n squared, because epsilon square is independent of fn minus 1. And so by these two properties is equal to 1. And so we get that it is exactly alpha 0 plus alpha 1 xn minus 1 square. Okay. So let us go to the next question. What is the next question? So it is some show that the volatility, okay, volatility is a term used to denote the variance of the price in finance. It's just volatility, which represents the risk of fluctuations, it is a measure of the fluctuations of the prices. So it is something that represents the risk that you have in the evolution of the prices of your financial market. And so we have to establish this recursive relation. And for that, okay, we compute this conditional variance. So maybe we can use these properties that we established here in order to compute this variance of xn. So if you look at this guy, the variance of y is equal to the expectation of the conditional variance. And if you put this guy on the other side, plus the variance of the conditional expectation. Okay, it is this formula that I will use. So if I use that, you see here, so what we did just before. So we have this expectation, which is 0, this relation. And now we know that the variance of xn is the variance of the conditional expectation plus the expectation of the conditional variance. Okay, it is by the exercise, I don't remember the number of the exercise, 7, I think. But we have seen that in the question 1, we have seen that this guy is 0. This was the question 1. So it is 0 plus, and this guy is exactly the guy which is written here. So it is yn squared. But this yn squared, we have seen that it was equal to that. So I can replace here by the question 2, it is expectation. Question 2, it is expectation of alpha 0 plus alpha 1 xn minus 1 squared. So what we get is that the variance of xn is equal to alpha 0 plus alpha 1 expectation of xn minus 1 square. But we know that expectation of xn minus xn or xn minus 1 is equal to 0. Why we know that? Because we have seen in question 1, we have seen that the expectation of xn given fn minus 1 is equal to 0. So if you take the expectation on both sides, you will get that the expectation of the conditional expectation, which is expectation of xn, is equal to 0. Okay, so in fact here I can replace this guy by the variance of xn minus 1. And I get as a relation, some simple recursive relation about the variance of my price at time n, in terms of variance of the price at time n minus 1. Everybody agree with that?
I do agree with that.
You disagree or you agree?
I agree. I agree.
I agree. Okay. Okay, it is clear for everybody? Okay.
Yes.
Yes. Okay, good. Okay, good. And okay, now you see it's not so much, maybe, I don't know if I have to finish this exercise because it's not probably not so interesting from the probabilistic point of view, is that now you have some arithmetical geometric recursive relation. So you can study the limit as n goes to infinity of a variance of xn. So for a long time, and this limit can be infinite or finite, depending on alpha 0 and alpha 1. But okay, I will not do it because it is maybe not so interesting to for this course. And so this is something that which is this kind of models are very used in finance to describe time series. Okay, more complicated models, but it is a basic one. Okay, so since it remains only a few minutes, let's show if we can do some exercise very fast. Some simple exercise. How is it?
Will it be something like the sum of geometric progression?
Yeah, yes, exactly. It is, but it is not a geometric one. It is arithmetical geometry. So you have first to solve the fixed point of this recursion. Okay, since I don't have time. Okay, I don't have time to too much exercise, so I can finish. I can explain you exactly what I mean.
No, it was just a question, yes or no. Okay,
Yeah.
I think.
Okay, if you have some problem, you can just ask me next time. I would show you, but in principle, I think you know how to do it. Okay. Well, no, this one is too complicated. Okay, afterwards, there are these things about martingales. Okay, let us try in a few minutes to try to do this exercise 10. So in exercise 10, you take some Markov chain on a countable set, a countable state space, E, which is countable, and with transition matrix P. So Fnx is the natural filtration of X. So it is sigma of x0, x1, x2, xn. And we take f, a function of from the state space E into R. And the first question is to show that the process MF, depending on this function f, which is defined by this formula, which is here, is a martingale respect to the filtration, which is here. So of course you don't have. So I recall you what is the definition of martingale. It means that what you have to prove is that M and F is in L1, so it is interval, first thing, and then you have to prove that expectation of Mn plus 1 F given Fn is equal to the expectation N and F. Sorry, no, I wanted to write without the expectation. Okay, this is the definition of a martingale. So in fact, there is a very strong relation between Markov chain and martingale, which is provided exactly by this formula. Okay, so I have to show that the MNF is a martingale. So the first point that it is in L1 is trivial because in fact the function f is assumed to be bounded. So if it is bounded, here at each time you have some finite sum of some bounded random variables, so it is integral. Now we have to show the second condition. So let me show it. And so f goes from E into R, bounded. And okay, so f and x is just sigma of x0 xn, where xn is just my Markov chain, and m and f is by definition is defined like the sum from k equals 0 to n of so how I define it. I don't remember if the sign was fxk. Okay, k equal 1. Yes. K equal 1 to n fxk minus pf of xk minus 1. Okay, so px, so here I am in some countable set. So pf, by definition, pf is p is just a matrix transition. This pfx is a sum over y in E of pxy f of y. Okay. So let us compute the expectation of m and f given fn minus 1x. So by definition, it is a sum from k equal 1 to n of f of xk minus pf of xk minus 1 given fn minus 1x. And here, as you can see, here I have everything with the sigma field respect to the process until time n minus 1. So I have to try to isolate in this sum what is measurable with respect to this sigma field. If I look at this guy, you see it depends on xk, but k goes from 1 to n. So if k is less than n minus 1, this random variable will be fn minus 1x measurable. But for k equal to n, it will not be the case. And here, k minus 1 is always less or equal to n minus 1. So here, this random variable will be fn minus 1x measurable for all k. So there is, to distinguish two cases here, if k is equal to n, in this first sum, if k is equal to n, and if k is less than n. So it is the reason for which I will separate this expectation of f of xn given fn minus 1x plus the conditional expectation of the sum over k equal 1 to n minus 1 f of xk minus pf of xk minus 1 given fn minus 1x. Okay, now this random variable, which is here, you see depend only on x1, x0, x1, x2, x3, xn minus 1. So it is measurable with respect to the sigma field until the time n minus 1. So I can rewrite it like, I can, in fact, forget this conditional expectation in the second sum. Okay, so I use the fact that if z is a random variable which is g measurable, then the conditional expectation of z given g is equal to z. It is a property that I used here. And now, so it remains this first conditional expectation. So if it is more clear for you, I can write it like, instead of writing like that, you can write it like that. The same as saying x0, xn minus 1. Okay, it is a different notation because it is just fn x is just the natural filtration. And you have to remember that xn is the Markov chain. So what is this guy? This is Markov chain. It is the same as the expectation of f of xn given the last state, xn minus 1. Plus this guy. Okay, because xn is a Markov chain. So it depends only on the final state, just before the state, the future after time n depends only on the past through the present, which is n minus 1 case. And now this one, you can write it like the sum over y in E of the expectation of f of xn given xn minus 1 okay, no, you can write it like, okay, that now you have just to use, in fact, how do you call it? The Markov property. By Markov property, this is exactly equal to pf of xn minus 1, sorry. Okay, plus sum from k equal 1 to this one of fxk. Wait, there's some guy which is missing here, no? Oh, sorry, I forgot some guy. Yes, here there is minus pf xn that I forgot. I decompose this sum from k equal 1 to n into the sum from k equal 1 to n minus 1 plus the term n. But the term n, there is f of xn minus pf of xn minus 1. So here, sorry, there is this guy that I forgot, which is here, which is also here, minus PF of xn minus 1, minus PF of xn minus 1. So at the end, you have some cancellation of these two terms, so it is 0 plus what's remain, which is exactly the martingale at time n minus 1. So we prove the equality between this guy and this guy. So we have a martingale. Is it clear? Or okay, just you see here I had the sum from k equal 1 to n. I decompose into I isolate the term corresponding to k equal to n, which is this guy, and the other terms which are from k equal 1 to n minus 1. And the term from k equal 1 to n minus 1, they are measurable with respect to the sigma field. So the conditional expectation, in fact, doesn't matter. It is the same as the random variable itself. But here, in the two first term, this f of xn is not fn minus 1 x measurable. So I cannot erase conditional expectation. But for this guy, I use the Markov property, which is here. And then I get exactly the same term. Then I subtract it here. So it gives 0, and you have a martingale. Is it okay for everybody? Yes?
Yes.
Yeah. Okay, so I will let you do the second, the second question at home, or maybe I will write it in the PDF. But okay, so maybe we can stop now just for 10 minutes, and I will continue afterwards, not with the exercises, but with the course on the Markov decision process. Sorry, somebody asked. Okay, no, somebody. Okay. Okay, so in 10 minutes we come back and we continue with the course.